Okay, hi folks. I just wanted to give you a quick video that may help you with homework C2, specifically problem 2. In both problems on the homework, I've tried to give you several hints as to where to look in the book for extra help, but I know that question 2 may be the one that is the most foreign to you, so I just wanted to give a little extra help on that. All right, so the point of this question is that we're going to draw. I've given you a bunch of random numbers, and the goal is to determine whether these numbers, which all are between 0 and 1, are uniformly distributed between 0 and 1. So um, as an example here, I can go into MATLAB, and so this isn't something you would do, but MATLAB has a pseudo-random number generator in it, and so I can say something like random unif 0, 1, 8, 1, which says give me 8 rows of one column, and I want them to each be uniformly distributed random numbers between 0 and 1. Now, it gives me these numbers, and I just take for granted that these are uniformly distributed between 0 and 1. But as we're going to learn in this chapter, it's not easy to generate random numbers that are uniformly distributed between 0 and 1. And if you can generate them, you can do lots of interesting things with them, which we'll learn about in the next chapter, chapter 8. But it's important to be able to test whether these random numbers are truly uniformly distributed between 0 and 1. So, right, now, as an example, I could have gone into MATLAB and I could have said, all right, what if I actually generate an exponential random variable with a mean of 0.5, and I'll generate, say, 6 of those. And so here you see I also get numbers that are between 0 and 1, but I'm pretty confident that these are not drawn from a uniformly distributed random variable because I asked MATLAB to generate them from an exponential distribution. But if you just look at them, I mean, how can you tell the difference between this list of 8 numbers and this list of 6 numbers? So, so that's the thing, is we're trying to build tests that help us give us a good handle, a good rigorous statistical handle on what is uniform and what is not. And then after the midterm, we'll actually start generalizing these tests to other distributions other than the uniform distribution. But for now, the uniform distribution is really important to us. All right, so let's forget about those numbers for just a second, and let me give you some quick background on what this Komogorov-Smirnov test is all about, the KS test, and how you're supposed to use it in this. So the basic idea in any of these frequency tests, so I guess I can put that term here. These are frequency tests. Frequency tests. That's the idea that I have, if I consider a number line, so I'll just draw a little number line here. And let's say that number line goes from 0 on this end to 1 over here on this end. And if I'm drawing random numbers, I know those random numbers are going to come up in between 0 and 1. But I need to know, do they come up in the right distribution? So are they all clustered around 0? Are they all clustered around the middle? Are they all clustered around 1? If they are truly uniformly distributed between 0 and 1, then if I draw enough of them, then they should be sort of found anywhere with equal probability along this line. So the way you do things in a chi-squared test is you would cut this thing up into equally spaced bins. So I could create a little bin like this big, another bin this big, and then another one. I'm going to maybe do like 4 bins. And they're not quite the right size, so I'll make them a little bigger, spread them out. So I'm going to put this one here, distribute these horizontally. Or maybe I need to make them a little smaller, but I hope you're getting the sort of the point here that I'm just trying to create little bins here that roughly represent, let's see, distribute horizontally here, arrange, distribute horizontally. All right, so basically what you can think of this is like, all right, well, if I put that's 0.25, and if this is 0.5 on the number line, and this is 0.75 here, then you can imagine I could take whatever numbers come out of my random number generator, I could put them in a box. If they're in this box, if they're from 0 to 0.25, in this box, if they're 0.25 to 0.5, in this box, they're 0.5 to 0.75, and in this box over here, if they're 0.75 to 1. And if this is if those numbers were drawn from a uniformly distributed random variable between 0 and 1, then I would expect if I drew enough of those numbers, then I'd get roughly the same count in each one of these boxes. So you imagine I could get like 5 numbers in this box, and 3 numbers in this box, and 6 numbers in this box, and 5 numbers in that box. And these all, if I drew 20, or in this case, I guess 5, 10, 19 numbers. So if I drew 19 numbers, then you could then ask a chi-squared test. Well, for 19 numbers drawn, if we assumed that these were all, that there's no preference for one of these boxes, then what's the sort of the likelihood that we would get the counts that we get here? And a chi-squared test would come out and basically give you a p-value that would represent whether or not these counts were likely to be from a uniformly distributed random number or not. So as an example, if it came out that I got 18 numbers here, 0 here, 1 here, and 1 here, well, in that case, the fact that almost all of my numbers are between 0 and 0.25 tells me that they weren't uniformly distributed. And so the chi-squared test should end up rejecting the hypothesis of uniformity. And so that's we call this a frequency test, because we're taking the numbers and we're converting them into frequencies. And so I might have had 18 numbers like 0, 0.1, 0.11, 0.125, etc. All 18 of those numbers were between 0 and 0.25, and I counted how many, thus the frequency, how frequently do I see numbers between 0 and 0.25. And in this particular case, they're sort of too frequent, and so this is probably not uniform, but you would imagine if this was more equal, then in those cases, then we might fail to reject this uniformly distributed hypothesis. So that's how you would do it with a chi-squared test. The problem with a chi-squared test is if you go down to having like 6 numbers, then it's the assumptions that make a chi-squared test work don't work anymore. And so that's why we end up going with something like a KS test, a Komogorov-Smirnov test, which operates in a very different way, but it still captures the same essence of it still is based on this idea of a frequency test. It just works differently. So the way a KS test works is you could say like, all right, well, what if I have, let's say 10 numbers. I drew 10 numbers. And so then after I drew them, I've drawn them, I sort the numbers. And so after I've drawn the 10 numbers and sorted the numbers, if they're uniformly distributed, then I might expect the first number to be roughly 1/10 in between 0 and 1. So if I were to draw that number line again, all right, so there's my number line. I have 0 on one end and 1 on the other. And I have these 10 numbers. So I guess I could just draw, maybe I will literally draw 10 little dots representing the numbers on this number line. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So then let's just say that I take these numbers that I drew. So this number, so this might have been 0.4, which is somewhere over here. This might be 0.12, and so on and so forth. So I'm going to spread these numbers out. So I drew these in some order. So they weren't necessarily already in smallest to largest order, but they were in some order. And if I were to place them on a number line and forget about when I drew them, then they would look something like this. So it might have been that I drew this number first, and then this number, and then this number, and so on. But once I place them on a number line, I kind of forget what order I drew them in, and I've effectively just sorted them by whatever value they are. So this one here, even though I might have drawn a 0.9 first, then I'm showing the 0.01 on the left-hand side because that's where it falls on the number line. Now, if these are uniformly distributed, and kind of like I think I've depicted here, then I would expect that the first number would be roughly in 1/10. So if I were to draw maybe the 0.1 on here, then I would expect that if things truly were uniformly distributed, then the first number would be pretty close to this interval from 0 to 0.1, since there are 10 numbers that were drawn, right? Because I'm dividing my interval into tenths. So 0 to 0.1, that's 1, all the way up to 1. So I now have 10 numbers in 10 boxes. So that's why this is a frequency test. Is instead of in a chi-squared test, I picked like 4 boxes so that I could get multiple numbers per box, because I need multiple numbers per box in order to make a chi-squared test work. But in a KS test, it's sort of designed for cases where it's very difficult to get multiple numbers per box. And so they just take that and go with it, and they say, all right, well, let's just take it to the extreme. If you drew 10 numbers, we're going to divide the number line up into tenths, and then see if you get each number in the box that you might expect it to be in if you had the uniformly distributed hypothesis met. So I can keep dividing this up, and so on. So this would be like 0.4, and then you can imagine 0.5, 0.6, 7, 8, 9, and then up to 1. And then for each point, I can say, all right, this point is because it is the earliest point in the ordering, I want to measure its distance from this box. And so I'm going to do that by measuring the distance from the upper bound and the distance from the lower bound. And I'm going to keep track of both of those numbers. The second one, I'm going to measure its distance from the box, from the upper bound and the lower bound. And I'm going to keep track of those numbers. Same with the third, same with the fourth. Now the fifth here, let's say this is 0.5. Now let's say this number that I drew, I would expect it to be in this box. But I can measure the distance to this one, but the distance to the lower bound ends up being negative because it's below the lower bound. Well, it turns out that I kind of focus on the maximum distance, and so anytime I get one of these negatives, I don't even have to do that calculation, and we'll see that in the table that gets built up. So basically, you can think of it as that if I were to draw a little box around each one of these, like these are kind of our areas of consideration, so maybe I'll make that translucent so we all can see it. All right, so the basic idea here is I've got these little regions of interest, and for each region of interest, I effectively am going to say what is the biggest difference from the dot that should be in that region and the boundaries. So this one corresponds to this dot, so I do that. And then if I were to draw the next region, this one corresponds to this third dot corresponds to this third region, so that's going to be the maximum distance, and so on and so forth. And then what I do is then I take all of those differences, and then I ask, what is the maximum difference of all the differences? And that will give me my test statistic. And so that test statistic, I'll be able to go into a table and look up to see if if it's too large. So if the test statistic is very large, then that means that one of my points was totally in the wrong box. It was just way outside of the box that it was supposed to go in. And so if that test statistic is sufficiently large, then we're going to fail the test and reject the hypothesis of uniformity. But if all of them end up producing a low distances, then my test statistic will be small, and it will be so small that it won't reach the threshold for rejecting the hypothesis, and we'll be able to conclude that we can't reject the hypothesis. That doesn't mean we accept the hypothesis, but it means we can't reject it. All right, so that is a rough overview of what's going to go on with the Komogorov-Smirnov test. Just in case there's some of you who just wanted to jump straight into the example without getting the background, then I'm going to stop the video here and I'll start a new video and we'll pick up where we left off in the Word document and we'll go through a quick example.